Hello friends, welcome to my channel. In today's video, I'm going to discuss something very interesting. That is the bound charges in the dielectrics. How this bound charges in dielectric gets generated at the first place. What is the mechanism of getting the bound charges generated in dielectrics? So let's try to answer this. What's a dielectric material? The dielectric material is an insulating material which doesn't have free charge to move because it's insulated, but it has a special property that when you place it in the external electric field, it can be polarized. That is, the electric dipoles can be generated in this material. There are various mechanisms through which this happens, but here we are going to discuss the most common mechanism of developing the electric dipoles in the dielectric when it is placed in the external electric field, which is common to all kind of dielectrics like polar, non-polar, etc. Suppose I have these two parallel plates which have been provided positive and a negative equal amount of charge by some battery of potential difference V. Now if I place a dielectric material between these two plates, suppose this is the dielectric material which I have placed between these two parallel plates. So this arrangement actually reminds me of a parallel plate capacitor having dielectric between these two charged plates. Now our concern is that what is actually happening inside this dielectric when it is placed between the external electric field produced by these two plates. Suppose this has a plus q charge on it and this has a minus q charge on it. So this arrangement has an electric field which is acting between the parallel plates, and in that very electric field this dielectric material is placed. So as such, as I have already stated, the dielectric material is an insulating material which doesn't have free charges to move. But when it is placed in the external electric field, dipoles may be generated in that. There are various mechanisms of depending on what kind of dielectric we are discussing to understand that how these dipoles are generated. But the very basic mechanism is that when you place it in the external electric field, then if we consider an atom inside this dielectric material, so this atom will have a positively charged nucleus which we have drawn like this, and an electron will be revolving around a closed circular orbit around this nucleus, as in the Bohr model. In actuality, this electron charge cloud is spread through this volume such that the center of the positive charge, that is of the nucleus, and this electron cloud, they coincide as in a neutral atom. Atom as a uh, whole is neutral, and center of positive and negative charge coincide. But what will place this atom in the external electric field? That is, when we place the dielectric in the external electric field, of course, this electrons and positive charge of the nucleus will feel a force under the impression of this external electric field. But since nucleus being very heavy in comparison to the electrons, that doesn't move significantly under the pressure of the electric field. What actually moves is these electrons get displaced from their place. So let's say in the figure that we have just drawn of the parallel plate capacitor, the electric direction of the electric field is this. This is, let's say, applied electric field E0 in this direction, and electron will feel of this dielectric material. The electrons here will feel the force in the reverse direction, because electron being negatively charged will feel the force towards positive plate. So in that case, what we see, actually the atom which was neutral earlier will remain neutral because charge cannot be created or destroyed, but earlier its center of positive and negative charges were coinciding, but now since there will be some displacement in the negative charge because electrons being light in comparison to the nucleus, they get shifted under the impression of this external electric field. So this shape will become little distorted, something of this kind, let's say. Okay, where this There's the negative charge here and the positive charge here. Uh, so now earlier these centers of positive and negative charge were coinciding. Now they have separated by a certain distance. Let me call this distance as delta, because D will be using for this dimension of this dielectric. Okay, so now suppose let's say the amount of this charge that we have taken is plus q here, sorry, minus q here and plus q here. So the dipole moment of such an arrangement will be q times delta. Okay, so in a sense, what we have seen here is that now the atom is considered as an electric dipole. Because what's an electric dipole? Electric dipole is that when you uh, have two equal and opposite charges separated by a certain distance, this arrangement is called the electric dipole. So the electric dipole moment for such an arrangement is P equal to Q times delta. Now what's interesting here is that now if we come back to our dielectric and try to see what will happen here. Now you see that every atom will feel the same force and will feel the same kind of effect. This is the picture. This is array of dots which I'm drawing. These are the neutral atoms before the application of the electric field. And once the electric field is applied, so the positive and negative charge get shifted. Now the positive and negative charge for this particular atom, which I'm marking here right now, again will be minus and plus. For this, if I do now the same job, minus and plus. For this, if I do, this will be minus plus. For this, if I do, minus plus, because every atom is similar. So now at this surface, the last atom, if I say, is minus and plus. So what we are actually seeing here is very interesting phenomena is taking place. That the positive of the first, let me number these atoms to make it more clear. Number one, number two. So the positive of the number one atom, which is this, is coinciding with the negative of the atom two, which is again on this. Okay, so in a sense, if we look here along this row, what is happening here is that net charge here at this point is zero, at this point is zero, at this point is zero, this is zero, this is, but at this surface, you see, at the two extreme ends of this dielectric, we get a non-zero charge. So similarly, we will have a positive charge here, and I have negative charge here on the surface of the dielectric. So what we have seen here, what we have achieved so far, I mean, through this discussion, we have been able to understood that despite not having any kind of a movement of the free charges in the dielectrics, we have been able to generate the positive and negative charges along the surface of a dielectric, right? And there is no charge inside the dielectric. There is no generation of charges in the bulk of the dielectric. Rather, on the surface only we get this kind of charges. Okay, so these charges here that are getting generated, this negative and these positives on the surface of the dielectrics, that is these charges I'm talking about here. So these charges are called as bound charges. Okay, or the polarization charges. Okay, these are called the bound charges or the polarization charges. Why polarization charges? Because they have been produced due to the process of polarization of the dielectric. Bound because they are not free to move, unlike electrons. When you place an electron in the external electric field or the conducting material, for example, in the external electric field, all the electrons, free electrons under the pressure of the dielectric material will keep moving until they cancel out the exact external electric field in case of a conductor. But here you don't have free electrons, you don't have free charges. Rather, what you have seen is that due to the polarization, we have been able to produce the bound charges on the surface of the dielectric, and these are called the bound charges, or the polarization charges. Okay, so now let's try to see that what is this. surface charge density, since this charge is totally on the surface, what is important to remember here is there is no net charge inside the bulk of this dielectric in this diagram. What we have considered so far, we'll consider the cases when there will be net charge inside the bulk of the dielectric. But right now in this, so far what we have considered is in this picture, that there is no charge inside the bulk of the dielectric. Okay, only charge present is on the surface of it. Okay, so let me call the surface charge density to this bound charge to be sigma b due to bound charges, and sigma free is the surface charge density of free charges on the plates, right? Because you see these charges that are there on the plates, if they have a, let's say, cross section area A, sigma free would be nothing but plus q by A. Okay, so we like to see that what is sigma b first of all. Now to look out the expression, to understand the expression for the sigma b, or to obtain the expression for the sigma b, we need to understand one more thing, that is that what is the polarization vector of a material. Polarization vector. So total dipole moment, this is polarization vector p, is defined as the total dipole moment per unit volume of the material. Okay, if we consider the bound charge is minus qb here and plus qb here, so this, according to this formula that we just learned, the dipole moment, total dipole moment generated inside the dielectric material will be qb times the distance between these two charges, positive and negative charges, which is small d, time upon the volume of the dielectric. Let's say the cross section of the dielectric is same as the plate, because we have considered this. Let's say this dielectric exactly fills the space between these two plates. In that case, the cross sectional area of the plates and the dielectric will be same, times d, which is equal to qb by a, which is nothing but equal to the sigma b, which is the surface charge density due to bound charge or bound charge surface density. So what we have obtained a very interesting and very significant result, that the magnitude of the polarization vector is equal to sigma b, or sigma b is in turn, in other words, is equal to p. So we can write down that sigma b in other words equal to p. Okay, that's very important. Okay, so this is the case when our direction of P, all right, is this direction, right, minus to plus. What is the direction of capital P? The direction of the capital is essentially electric dipole moment. Electric dipole moment has a direction from negative to positive. So this is the negative charge, this is the positive charge here. Uh, this is the negative charge we're talking, and this is the positive charge. So direction will be negative to positive, right? And the area, cross-sectional area, if we cut this dielectric this way, let's say this, and consider the cross section, the area vector is also in this direction. So that's why we are getting that sigma b is equal to p. But suppose our case is something like this, when our this is our, like, say, dielectric, and having this oblique cut, the ends are not sharp straight cut, they have some at angle, so that the area vector is, let's say, n hat, and the polarization vector p is in some direction and having angle theta. In that case, the general expression for sigma b will be, we have to consider the p which is along the area vector n hat, so p dot n hat. So that will be the most general expression for sigma b. Okay, so that is the so far about the bound charges and the polarization vector, and what is the relation between the polarization vector and the bound charges. Now we can continue our discussion. We can quickly discuss one or two important observations that we have seen. The first of all, let me remind you the key point. The foremost important thing is that the whole result of this mechanism of polarization of a dielectric is nothing but to have a surface charge, which we have calculated as surface charge as the sigma b, right, on the surface itself. There is no charge in this condition what we have considered so far, where this capital P is uniform through the dielectric. There may be cases when this capital P is non-uniform, because this capital P essentially depends on the electric field, net electric field inside the dielectric. So sometimes it may be non-uniform. In that case, what will happen, that will have a non-zero charge present in the bulk of the dielectric, that is in the volume of the dielectric itself. We will have some non-zero charge, but here in this case we have considered the uniform P. So in this uniform P, what we have observed here is that no charge was there inside the bulk of the dielectric, that is in this region there was no charge. There was no charge. Whatever charge is there, that was on the uh, edges of the dielectric, on the surface of the dielectrics, and it gives an impression as if certain amount of charge have moved from one end to the another end, although in actuality there is no movement of charges, because there is no free charge available here, and in reality no charge has moved from one end to another end. But this whole process has given the conclusion or the impression like that, that as if some amount of charge has moved from one end to another end, and that's the reason why you have the bound charges at the first place in the dielectric. Okay, so I will talk about now more about the cases when P is non-uniform. When you have non-uniform P inside the dielectric, so what will happen in that case? So you see, when you have, P is non-uniform, means suppose this is my dielectric, and my P is non-uniform, that is it is changing from every place to place. That may show it by arrow, and this magnitude of this arrow is, let's say, changing, okay, from point to point, from different location in dielectric. So what will happen here is that if it is the case, right, the P is essentially nothing but the electric uh, P is the polarization vector, which is because of the electric dipole moment. So that will be different from different place when we have, let's say, for example, different charge in atom. Let's say you have the extra charge coming every time when this magnitude is increasing. Let's say you have earlier you have minus q under the impression of the external electric field, which was in this direction, the negative charge, and the plus which are then you, when you the another atom get displaced, you have a minus here and plus here. So this plus and minus now, which was cancelling earlier in the uniform P case, will not cancel anymore, right? Because they are not equal and opposite. They are not equal in magnitude, right? Plus charge could be lesser than the minus. Okay, so this cancelling business that was there in the earlier case, let me redraw. So there was this cancelling business, this minus, plus minus, right, and so on and so forth, and then there was plus. Similarly here, so this cancelling business of equal and opposite charges will no more take place because of the non-uniformity in capital P, the polarization vector. So in that case, what will happen? We will have a non-zero value inside the bulk of the dielectric as well, of the charge. Now charge, because they are not equal, right? This plus is, let's say, plus q, some plus q. This minus is, let's say, some minus capital Q. So there is imbalance of charges. So there will no charge neutrality inside the bulk of the dielectric. Rather, there will be some non-zero charge available in the volume of the dielectric, and there will be, of course, charge density on the surface as well, right? Sigma b, some sigma b, and there will be some rho b also in that particular case when P is non-uniform. Okay, in when P is non-uniform, so we'll have some. We'll have sigma b as well as rho b. Rho b is the volume charge density, volume bound charge density. Because there will be non-zero charge present inside the volume of the dielectric, right? Which is because of the non-uniformity of P. So in that case, we'll have both the surface charge, bound charge density, and the volume charge density. I think it's clear. Let me repeat why there is a generation of charge in the volume of the dielectric in case of P is non-uniform. And P is non-uniform, then this charges that were cancelling each other earlier when P was uniform, that will not take place because now the value of P is changing from point to point, right? So equal amount of magnetic electric dipole moment will not be there, right? Equal amount of charges will not be uh, at the different places. This will not cancel out exactly the positive and negative charge at a particular point, then which will which will lead to some non-zero volume charge density inside the bulk of the dielectric. Okay, so now the question is, so what is the situation like? Situation is like that some charge of from the volume has moved to the surface now. Earlier, if we look at here in this particular picture, the charge has moved from one end to another end. And you have a net surface charge, and there was no charge inside the bulk. But now you have a charge inside the bulk of the material as well, and on the surface of the material. Now the material itself is electrically neutral. It will remain electrically neutral even after this mechanism takes over. It means that if the positive charge has moved out to the surface, then there will be a net negative, equal and opposite negative charge inside the volume of the dielectric, right? So there will be a different charge polarity which is present inside the volume to the charge which is present on the surface of this dielectric in the case when P is non-uniform. That's very important to understand. Like if in the bulk there is a negative charge density inside the bulk, so there will be a positive charge density present on the surface. Let me redraw the diagram. Let's say this is my dielectric here, dielectric material, and if I choose, let's say, some volume of this, some volume arbitrary, and P is non-uniform, let's say, everywhere now. It's non-uniform, it's not same, right? So then what will happen? Some charge will move out from this volume to this surface, right? And let's say this positive charge has moved out on this surface, and there will be a net negative charge in the volume of this figure of this element that we have just drawn, right? That is in this area. There will be net negative charge. So this is about the polarity. But what about the magnitude of these charges or the amount of? They will be exactly equal because overall the material has to be charge neutral. So that is if sigma b is the surface charge density, let's say this surface that we have just drawn here, and d is this small element of the surface, and I integrate all the entire surface. So this gives me the total charge on present on the surface. That has to be equal and opposite to the charge which is present in the volume of the surface, equal and opposite to the charge present in the volume which is engulfed by this surface that we are talking about, this S. Okay, so if I integrate the charge present in the volume which is minus here, then I should get the same amount of charge, but the polarity will be opposite, right? So if sigma b is, we have just seen in the previous cases, p dot n hat, right? If I write this, I can write like this, n hat I have observed with the area vector, because n hat is nothing but the direction of the area vector, and this is rho b d tau. Now I can actually use the Gauss integral theorem, and I can convert the surface integral into the volume integral by taking the divergence of this P. Okay, so if I compare these two relation, I get that rho B is negative of del dot P, the polarization vector. Okay, this is an again very important result that we have obtained. So in case of non-uniform P, when the polarization vector is non-uniform, we are going to have both kind of charge density, bound charge density, the volume charge density, and the surface charge. The charge will be present on the surface as well as the volume of the dielectric. Okay, so that's the important result that we. Now, having understood all these things, now it's good time to discuss the Gauss law in dielectrics. How the Gauss law will look like in case of dielectric. So we know what is the Gauss law. Gauss law is del dot E is equal to rho upon epsilon naught. This is the differential form of the Gauss law. In case of dielectric, this rho, which is the volume charge density here, we have just discussed that the bound charges can be present in the volume of the um, specimen, dielectric specimen. So in the case of dielectric, this rho actually could be rho B, the bound volume charge density, plus rho free. Rho free means there could be some extra charges present in the volume, which is not there because of the polarization, like certain ions are there. There could be some other charges like ions present in the bulk of the dielectric, which is not there because of the polarization mechanism that we have just discussed. So rho free here is the free charge volume density that we, and that when we can say that free means whichever charge is there, that is not because of the polarization process. Okay, so whatever charge is there, uh, not because of polarization, so we'll call that charge as free. So this equation 1, if I say, will read in case of dielectric del dot E is equal to rho B plus rho free upon epsilon naught, which is equal to del dot epsilon naught E uh, minus rho B is equal to rho free. Now, we have just seen that rho B was equal to negative of del dot P. So I can put the values here, a value here, and I can write down this relation as plus P is equal to rho free, which is equal to del dot. So this vector here is defined as the D vector, and which is known as the electric displacement vector D. D here is epsilon naught E plus P, and this is known as electric displacement vector. And this form of the law is known as the Gauss law for dielectric. Okay, this rho free is the free volume charge density, and I have already explained the meaning of free. Free means in the case of dielectric, which is not there because of the polarization process. Whatever charge is there, that will be termed as free, maybe in the presence of the ions or maybe from the other source, but not due to the polarization. So free volume charge density, and this is the Gauss law for dielectric. Okay. Now, if we consider this electric displacement vector D, which is epsilon naught E plus P, so P is actually proportional to E. Uh, so, what is E here? E is the electric field, net electric field inside the dielectric. Net electric field inside the dielectric means, remember, we had this diagram, right? I coming back to this diagram. So you see here we have a positive charge here and the place and the negative charge on this plate, and in the dielectric we get, finally, due to this polarization process as a mechanism, we get the negative charge on the surface and the positive charge on this surface. So this negative and positive charge in turn means that it will have its own electric field, which is in the reverse direction of the applied electric field, right? So let's say this is E1 in this direction. That is because of the bound charges. Okay, or let me call EB if you wish to distinguish due to the bound charges. EB in the reverse direction. So this E here is actually the resultant. It is the resultant of E0 and B. Yeah, resultant of E0 and B. EB. Hmm, right. So P is proportional to E, and that is equal to a constant. This is known as epsilon 0 chi E. Epsilon 0 is the, of course, permittivity of the free vacuum, and chi here is known as the electrical susceptibility. Electrical susceptibility. This is the measure of the fact that how easily a material can get polarized, right? Right. So now, if I place the value of this P in the relation D equal to epsilon naught E plus P, I'm going to get epsilon naught E. So this E here is the same E that we have been talking about, right? This E is inside the dielectric, right? Okay. So del E plus P is epsilon naught chi E, and we are going to get epsilon naught 1 plus chi E. Okay. Which is can be written as epsilon E, D is equal to epsilon E, or in other word, epsilon is equal to epsilon into 1 plus chi, where epsilon is the permittivity of the medium, of the dielectric, permittivity of the medium, which is our dielectric in this case. Okay, and which is equal to epsilon 0 plus into 1 plus chi, where epsilon equal to epsilon 0 can be termed as the relative permeability with respect to the vacuum 1 plus chi. Okay, here one thing I would like to add that i- in few books this expression here is written as P equal to chi E. They don't write this epsilon naught. Right, in those notation, this chi will have a dimension. In our notation, however, this chi is a dimensionless quantity. Okay, so don't get confused if in some book you see this suspicion as p is equal to chi. It means that chi is have dimension. Right here, we have introduced our chi is pure constant. Right, it's dimensionless and it is termed as the electric susceptibility. So yeah, that's it for now.